In this video, we're looking at Newton's law of cooling, but we're taking a precalculus perspective. We won't look at the differential equation that sets up the actual formula for Newton's law of cooling, but we will solve the exponential equations. Newton's law of cooling arises from the observation of a situation where we take some object that has some temperature and we put this object into a place that has a different temperature. And the rate of change of the cooling of this object, if we place a hotter item into a cold environment, the rate of cooling is proportional to the difference in temperature of the item compared to its surroundings. The greater the difference in temperatures, the quicker it cools. The classic example for this type of a problem is a cup of coffee in a room. How quickly will it cool? And this observation tells us that a hotter cup of coffee cools more quickly than a cooler cup of coffee would. From this observation, we would use calculus to set up a differential equation that leads us to understanding that there is this e to the x exponential part of the function that will tell us our final temperature. Now let's look at the graph of this function, f of x equals e to the x. Here's a graph of this function, f of x equals e to the x. Now this graph is increasing, so this is not exactly the basis that we want for our formula for Newton's law of cooling. We would like to see something that is a decreasing function. If we use a negative exponent, now we have a decreasing function. So we will be building off of this e to the negative x. Let's expand this idea a little bit further. Let's try to use that e to the negative x function, but apply it to a situation where we have a cup of coffee that is 100 degrees Celsius, and we're placing it in an environment that is 0 degrees Celsius. So our e to the negative x function, which cross the point 0, 1, is not going to be an effective model for this situation where we need to have a cup of coffee that begins at 100 degrees. Well, let's use our knowledge about transformations, and now multiplying e to the negative x by 100 has a result of this vertical stretch. So now our y-intercept is not at positive 1, it is at 100. So now we can begin to see a model of this cup of coffee that begins at 100 degrees Celsius and then cools, and eventually will get closer and closer to its surrounding temperature of 0 degrees. But the actual speed at which it cools can depend on a lot of different things. For this example, it might make a difference if we have a cup of coffee that is in a thermos or some sort of insulated cup, or if it's in a paper cup. It might depend on the humidity of the room or some other factors. So we need to be able to adjust the speed, this actual rate of cooling. If we keep thinking about transformations, then changing the speed, basically how quickly does this graph decrease and then begin to level off, is a matter of horizontally stretching or compressing. So we will be multiplying our variable x by some factor. Right now we are looking at this function 100 times e to the power of negative x. Now we've added the function f of x equals 100 times e to the power of negative 0.75x. The coefficient of x, we have now made it less negative. We've made it closer to 0. So our rate of cooling has been slowed. It is not cooling as quickly now that we have made this coefficient less negative. If I need to model a situation where it cools even more slowly, I'm decreasing this rate, but I'm careful when I say that because we are talking about a negative exponent because it is a decreasing function. So when I say smaller, I really mean closer to 0. The closer we get to 0, the more smooth, the less steep this curve will be. Let's look at one more where we decrease the coefficient one more time. Now here is a function 100 times e to the power of negative 0.25x. And it is decreasing at a much slower rate. Now what if we needed a function that would model things cooling very, very quickly? Maybe you have a guess that our coefficient would become a more negative number, further from 0. And we see this function in red is 100e to the negative 2x. So as we do problems with Newton's law of cooling, we will need to figure out what is our rate of cooling based on the information that's given. But before we get into solving an actual problem, let's deal with the graphs a little bit more, because right now we have a few models of a cup of coffee that begins at 100 degrees Celsius, it's placed in a room that is 0 degrees Celsius, and over time the temperature of this coffee cools and eventually becomes closer and closer to the temperature of its surroundings. But what if our surroundings are not 0 degrees? What if our surroundings are 20 degrees and that we want our function to level off at 20? How would we make that function? Well, we want to shift everything up vertically. We want our function to level off not at 0, but at 20. Shift everything up by 20, and a vertical shift means that we are adding something to our function. I'm going to pull off just one of those models for us to continue using for an example. I use 100 times e to the power of negative 0.5x. Now let's incorporate this vertical shift of 20 units. Our entire graph is shifted up 20, and we can see that we are leveling off now at 20. I'll even add in an asymptote here at y equals 20, and we do see our graph leveling off. But what has happened to our y-intercept? Since everything has been shifted up, now we see that our coffee, according to this function, is starting at 120 degrees, but we want to keep our coffee at 100 degrees Celsius. We don't want to shift the entire thing back down. We need to not do any more shifting. We need to do some vertical compression. Our coefficient on the exponential expression is currently 100, but we should not automatically use our starting temperature as that coefficient. What we really should think about is the difference in our temperatures. Our coffee starts at 100 degrees. The surroundings are 20 degrees. So the amount that this is going to change is really only a difference of 80 degrees. So that's our final move to this function, so that it will actually begin at 100 and it will level off at 20, is to say make the coefficient not 100, not our starting temperature, but make it the difference. So we will be using 80 degrees because that is the difference of the cup of coffee at 100 and the environment at 20 degrees. There's that function f of x equals 20 plus 80 e to the negative 0.5x. It meets those constraints that the cup of coffee starts at 100 degrees. Remember that our horizontal axis is time. So at time equals 0, which is the moment that we put this cup of coffee into its environment, it is at 100 degrees. And as time passes, it cools and eventually gets closer and closer to its surrounding temperature of 20 degrees. Here we're looking only at that function, which is modeling a cup of coffee at 100 degrees, cooling to 20 degrees, but now we've made an assumption about its rate of cooling. We are using, in our exponent, a coefficient of negative 0.5. We could say that k equals negative 0.5, but we don't want to make the assumption that that will always be our rate. We need to incorporate some given information to determine what is the rate of cooling in the particular problem. I want to look at the graph for a little bit longer just to give you an idea of the approach to these problems that we will use. We will use information like what is the temperature of our environment, and we will know that that temperature is the leveling off temperature. We also know that this is our vertical shift. We will be adding this temperature of the environment to the function that we create, which will model our temperature over time. We'll also be given information about our starting temperature. We could think of it as one point of this function, but we don't yet have enough information to know exactly how this graph will look. We know that it will cross through this y-intercept at 100 if that is our starting temperature. We know it will level off, but we don't yet have a sense of our growth rate, if it will cool very quickly or if it will cool more slowly. We need to incorporate more information given to us in the problem. That piece of information would be something like, after 9 minutes, the temperature of the coffee is 24 degrees. We have that point plotted here. Now we know 2 points that our function must cross through, and that is enough for us to determine our growth rate. We must incorporate e as the base of our exponential expression. Here's that function put back. F of x equals 20 plus 80 times e to the power of negative 0.5x. It meets our constraint that the initial temperature is 100, and it does level off at 20, but it does not cross through this ordered pair. It means that our growth rate is not accurate. What we have currently, it is cooling too quickly. We need it to cool a little more slowly. We're changing our growth rate, the coefficient in the exponent, we need to make it closer to 0. So let's take it from negative 0.5 down to negative 0.4. Looking at this function where our growth rate is negative 0.4, it is cooling more slowly, but we're still not slow enough to reach this point where at 9 minutes we are at 24 degrees. Let's change that growth rate from negative 0.4 down a little bit further to negative 0.3. Now we have a function that does cross through both ordered pair solutions. Now that we know this function that is an accurate model for the cooling, we can answer other questions like, how long will it take for this cup of coffee to reach 22 degrees? Now we can answer additional questions after we have found what is the growth rate. Graphically, if the question was, how many minutes will it take for the cup of coffee to reach 40 degrees, I would just find on our function, remember it's this last function that is our model, at 40 degrees, it looks like that would take approximately 4.6 minutes. We will do some similar moves when we solve these problems algebraically. We will find the characteristics like our starting temperature, the temperature of the environment. We will need to do some calculating when it comes to finding the growth rate. We won't take the approach that we did here where we just try different values of k until we find the one that fits the ordered pairs. We will do that part algebraically. But what we can do at this point is come up with this function. A function that will give us our temperature as a function of time. Think about the transformations we've talked about so far. Shifting up vertically was our temperature of the environment. Let's call that T0. And what we add to this is the difference in temperature. Let's call our item T1. So the difference in temperature would be T1 minus T0. And this difference is multiplied to the exponential expression e to the power of, we can make this negative because we know it's a decreasing function. There's our variable time, and what we'll need to do, very similar to how we just broke it down here, know the temperature of the environment, know the temperature of the object, figure out the growth rate, and then we can answer some further questions. Here's the example that we will work algebraically. A cup of coffee is 86 degrees Celsius. It is placed in a cooler that is 10 degrees Celsius. After 8 minutes, the coffee is 39 degrees Celsius. What is the temperature of the coffee after 12 minutes? Let's set up this function first. The temperature as a function of time will be first our surrounding temperature, that's the temperature in the cooler, 10 degrees, added to the difference of temperatures, the difference of our coffee at 86 and the cooler at 10, multiplied by our exponential expression. Now currently we do not yet have enough information to know our growth rate. And it's a function of time. We'd like to keep that variable t in there for right now. How will we find our growth rate? That's where we will incorporate the next piece of information. After 8 minutes, the coffee is 39 degrees Celsius. I've put that information into our formula, that we will reach a final temperature of 39 degrees after 8 minutes, when t equals 8. And now we have an equation that has only one unknown, k, our growth rate. Here's how we are going to algebraically find our growth rate. Our variable is up there in the exponent. We will need to use a natural log at some point. Before we get to the natural log, I'd like to try to isolate this exponential part. I'm going to keep working to isolate this exponential part and now divide both sides by 76. I want to take this opportunity to caution you about rounding. It's my advice that you round only at the very end of a problem. So the 29 over 76, I will not divide and round this into a decimal. I'm going to keep it as an exact answer as this fraction. This exponential equation is equivalent to this log equation, and I'll finish solving for k. Here's my exact answer for the value of k, our growth rate. We could at this point look at that decimal approximation just to get an idea of what that number is, but for the rest of this problem I'm going to try to use this exact expression for my value of k. Here's our model for this situation. I've put in that big chunky expression. I wouldn't say that you need to necessarily rewrite your equation this way, but I would encourage you to have the calculator do all this work and do not do any rounding until you get to the end of the problem. Now, how should we answer this last question, what is the temperature of the coffee after 12 minutes? That's just a question of evaluating this function at t, little t, equals 12. I'll put this entire expression into the calculator. Be careful about order of operations and using all the parentheses to make the calculator do the operation exactly the way we want it to. I come up with a value that is approximately 27.9 degrees Celsius. You may have a calculator where you are comfortable entering this entire expression in, but what I like to do, actually exactly what I did for this problem, was I did natural log of 29 over 76. Make sure that your natural log is on the fraction, so you might have to use parentheses there. I kept that final value in my calculator and then did divided by -8. I kept that entire value in and just did times 12, and then e to the power of negative that answer, and then multiply by 76, and lastly add 10. A quick recap of our steps through this problem. We needed to observe some key pieces of information: our starting temperature of the item, our temperature of the environment, and one more piece of information that will serve basically as an ordered pair to let us figure out what is the value of k needed to model this particular situation. And once we have that, then we go to part 2, where we actually begin to answer the question asked based on the value of k that we found.